Chan is assistant professor, is ours, assistant professor in our department. He's in AI sub-area, machine learning, but I think machine learning and AI today is almost a synonym. What is AI without machine learning? I don't know. Okay. So, and he's investigating, his main area is investigating the theoretical foundation of deep learning. In the title, in the bio, he wrote non-convex. This goes without saying. If things were convex, we know we don't need machine learning, we don't need convex things. We knew how to deal with many, many, many decades ago. So he comes, if he hanged all these awards like a soldier yesterday, Memorial Day on his shirt, it will be full. Yao Academic Career Enhancement Award, NSF Career, this is huge, NSF Career, Simon Institute Fellowship. So you really were there for a year, or how long have you been in the Simon Institute, Chan Chan?
I was there for the summer, for the entire summer.
For the summer, okay.
Yeah.
Summer, so it's a summer fellowship. And then all the industry gave him research award, Adobe, Salesforce, and Amazon Web Services. So only Google is missing. So do something about it, Chan Chan. And he will talk to us about machine learning of epidemic COVID-19 forecasts. I don't know what is so special. We will see if there is something special about COVID-19 forecast, but epidemics to me was always completely something statistical, purely statistical. So this is the first time that I hear machine learning and epidemiology. So it will be very interesting. I present Chan Chan for you.
Okay. Yeah, thank you, Lee, for the very nice and long introduction. Today is my great pleasure to be here to share with you some of our recent progress using machine learning to forecast the spread of the coronavirus and also to predict the future of our the country and the states when we are hit by COVID-19 and during this very critical time. So as Ali mentioned that in terms of academic knowledge, actually, there must be something about the statistical learning or statistics underlying. That's pretty true. So actually, the machine learning I'm going to talk about today is mostly statistical machine learning. So it's based on statistics. It's not based on deep learning. The reason why I prefer to use statistical machine learning to solve this problem is because I want to use some like white box machine learning instead of black box machine learning. Okay, so you will see more details about the machine learning approach we are using to do this kind of forecast. So the first question is, what is COVID-19? I think everyone in this talk should have already know COVID-19 pretty well because we are hitting by this disease really hard in the past few months. So according to CDC website, so COVID-19 is an infectious disease caused by the recently found virus known as SARS-CoV-2, or you can call it the coronavirus. Okay, so this is a very novel and very new virus that we don't have a very good knowledge about this virus. And that's why the challenging we are facing. We don't have the vaccine for this virus yet. So before we get a very good treatment and also the vaccine for this disease, we need to make sure we understand the spread of this virus and be able to either contain or mitigate the spread of this virus. So as of today, if you look at the number of confirmed cases in the world, okay, there are about 5.6 million people in the world diagnosed as COVID-19. So this is only the reported number of cases. As I will mention later, there are many, many unreported cases because of the capacity of testing. So you should be more careful about those numbers you see in different places, because in my opinion, all those reported numbers are underreported, okay? But even for this underreported number, it's already a huge number. It's like 5.6 or close to 6 million in a few weeks. And there are 349,000 people died from this disease across the world, okay? And the number of people recovered from this disease is about less than half. So we are still in the early stage of this disease, in my opinion. So that's why it's pretty important to forecast the future spread and also the future progress of this disease. The case fatality rate, based on these numbers, actually you can calculate the phase fatality rate, which is the number of deaths divided by the number of confirmed cases. So the rate for the global rate actually is about 6.19%. Okay, so which means for about every 100 people who got affected by this disease, there are about 6 people later will die from this disease. But on the other hand, this is called a case fatality rate, because this is based on the reported number of deaths and the reported number of confirmed cases. Since there are many unreported cases, so when you are calculating the real fatality rate, or sometimes called the infection fatality rate, that rate will be much lower than this one, because you are going to divide the number of real number of deaths divided by the number of real confirmed cases. So that number will be lower than this one. And for United States, as you can see, as of today, there are about 1.7 million people getting affected by this disease. And the number of deaths just surpassed 100,000 just 2 days ago. Okay, so and there are less than about a quarter of the people recovered from this disease. Some of them get some medical treatment in hospitals. Some of them, they just recover by themselves. And the case fatality rate in the United States is about 5.8%. It's lower than the global rate. Okay, but it's not much lower than the global fatality rate. Now let's take a look at the situation in California. So in California, there are about 69,000 confirmed cases, among which there are about 4,000 people, less than 4,000 people died because of this disease. The case fatality rate in California is about 3.9%, which is lower than the case fatality rate in the United States. But this rate is still relatively high compared with many other states that are not hit by coronavirus that severely. Okay. And finally, let's look at the situation in Los Angeles. So in Los Angeles, as of today, there are 46,000 people diagnosed as COVID-19, which actually is almost half of the confirmed cases in California. So that's why I would say Los Angeles is indeed a hot spot for COVID-19, because the number of confirmed cases in Los Angeles is almost half of the number of confirmed cases in California. And if you look at the number of deaths, okay, it's more than 2,000 people died in Los Angeles because of COVID-19. Actually, it's more than 50% of the deaths in California. Okay, so if you look at the case fatality rate, is about 4.6%. Okay, it's higher than the case fatality rate in California. So we are really facing a big challenge in Los Angeles because, and some people may say that we have more confirmed cases because we are testing more aggressively and more proactively. That's true, because when we have more and more testing, then we will have a better understanding about the current situation of the COVID-19 disease in Los Angeles.
Kwakwa, I have a question.
Sure, go ahead.
When you say recovered, you probably mean recovered means, to me, recovered means of those that were hospitalized, 18,000 recovered. So it doesn't mean, because recovered is those that had the corona and they had the COVID and didn't die. So you don't mean recovered by the recovered mean, you mean of those that hospitalized, 4,000, let's say in California, 4,000 died and 18 left the hospital. So recovered is left the hospital, right? That's what I mean. But because the difference between confirmed and death is recovered, isn't it? Which is 92,000.
So the difference between confirmed, so the number of confirmed cases minus the deaths, minus the recovered, this is called the active cases. So active cases means those patients, some of them are still in the hospital, and some of them, they are not hospitalized. They just got some treatment and they are doing, for example, quarantine or isolation at home because they don't have very severe symptoms, so they don't need to be hospitalized. So here the recovered actually include those people who got discharged from the hospital, and also patient who didn't get hospitalized, but they, for example, stay at home, receive the medicine from doctors, and after, for example, a few weeks, they fully recovered from the disease.
So you don't mean that about 70,000 people are still in the hospital? Are still
Oh, no, definitely not. The number of people in the hospital are only those people who are still who still have the symptom and who are in a very severe situation. Only in that case, they are in the hospital or even in the ICU. But you know, many people with mild symptoms, they are not hospitalized.
Okay.
Yeah, I think we got another question from Wei. Hi, Wei, do I need to unmute you? Okay, so I don't know how to unmute the participant. Maybe I will just
click on the side, on the left. Click
on the left.
Click on the left.
Click on the slide on the left that you want to show. Go on the left. Click on the. You were in the below that.
Oh, okay, I see. Yeah, because I saw someone raise a hand, so I thought I might want to unmute. But I don't know how to do that. Osana, do you know how to do that?
It looks like Osana is not there.
Okay, that's fine. Maybe let me move on, and then later I can take more questions after I finish this presentation. Okay. So in response to this COVID-19 pandemic, there are a lot of public health interventions being issued and implemented at different levels, including the national level, the state level, and also county level. So these public health interventions include travel restriction, social distancing, stay-at-home order, contact tracing, quarantine, isolation, and also wear mask and face covers in the public place. Okay, so these are those responses done by the federal government, the state government, and also the local government, as well as local Department of Public Health. So as a computer scientist and a machine learning researcher, AI researcher, so when we first went into this COVID-19 pandemic, the first question I asked myself is, what can I do, or what can we do as a computer scientist and also as a machine learning AI researcher to help combat or contain the COVID-19 pandemics? So there are a list of things I came up, including using AI to model and forecast the spread of COVID-19 and design some sampling and testing strategies to understand the prevalence of COVID-19 in different states or in different counties, as well as doing, for example, using AI and machine learning to design a new drug or to discover a new drug, or do some kind of drug repurposing. For example, there are some existing drugs used for other disease, and maybe it is effective for curing COVID-19. And the last thing I came up is we can use computer vision or AI technique to diagnose the CT or chest X-ray images for COVID-19 or potential COVID-19 patients. Okay, so these things are those things I think we can do, and we can benefit from using AI and machine learning techniques. And I started with the modeling and the forecast task, because that's the task I think I will be in a very good situation to do that, because it's more or less about how to combine the epidemiology and the machine learning together to understand the spread of COVID-19. So in this talk, I will focus on modeling and forecast. And for the other tasks, although I haven't really started to work on that, but I believe some of my colleagues, they may already started to look into those problems. And I'm more happy to discuss offline and do and have more collaborations if there's a good opportunity. So we launched the using machine learning to combat COVID-19 project on March 28th, about 2 months ago. And you can go to this URL to our website. So it's a very comprehensive site, which contains a lot of functions, including peak prediction, also preference prediction, and many other things we have keep adding into this website. Okay. So later, after in the end of this talk, I will go to this website to navigate you through the website to see a few things that I think might be useful for COVID-19 forecast. So in today's talk, I will be focusing on the following objectives. The first is how to forecast the number of confirmed cases as well as deaths caused by COVID-19, and how to estimate the peak date of active cases in the country and in different states, and how to estimate and track the basic and effective reproduction number for COVID-19. So you probably heard of R0, right? So if you read the news articles, people are talking about the R0, which is the reproduction number, the basic reproduction number. And this is a very important quantity which tells you at which stage you are in this pandemic. If R0 is greater than 1, then that means the number of confirmed cases will increase exponentially. And when the R0 is less than 1, then that means you somehow pass the peak, and the number of confirmed cases will decrease in the long term. Okay. And finally, I will talk about prevalence estimation. prevalence means how many people got affected by COVID-19. So this includes both the individuals who are tested as positive, as well as many asymptomatic patients. For example, many people due to testing capacity or due to the very mild symptoms, so they didn't go to test themselves. So even they have exposed to the virus, and even if get infected by the virus, but they don't know they are COVID-19 patients. So by doing estimation of the prevalence, we will have a very good understanding about the ratio of the population that are affected by COVID-19. And this is related to the so-called herd immunity, because we know if the prevalence is about 67% of the population, then we basically get herd immunity. So I will start with the first task to forecast the number of confirmed cases and deaths for COVID-19. And this is the result we want to deliver. So on the left, I show the number of confirmed cases in the United States. The solid line is the number of reported confirmed cases. And the dashed line is the number of projected confirmed cases. And in addition to provide some point estimation for the projection, we also want to deliver the confidence interval to assess the confidence of our projection, because this is important. If we don't provide you the confidence interval, then this kind of projection is not very trustable. Okay. So we provide a 95% confidence interval, which tells you the upper and lower bound of our projection, in addition to the mean of the projection. And on the right, in addition to the projection of confirmed cases, we also provide a projection for the deaths, okay? And we also provide the 95% confidence interval for our projection, for death projection, okay? So this is the result we are delivering on our website. So next, I will show you how did we generate this kind of projection. Okay, so we are using epidemic models as well as machine learning to generate this kind of projection. Okay, so when people are talking about epidemic modeling, people often mention these two very famous models. The first model is called the SIR model, which is susceptible, infectious, and removed. Okay, so for the removed compartment, is sometimes also called recovered. Okay, so here I chose to use removed because it includes both recovered as well as death. Okay, so I think removed is a more accurate name for this compartment. So SIR model has three compartments. Okay, so it basically divided the population into three groups. Okay, so within each group, there are individuals that belongs to this group. For example, in the susceptible group, it contains those individuals that are under the risk of being affected by the COVID-19. And in the infectious group, those are the individuals who have already got affected by COVID-19. And in the removed group, these are people who either recovered or died from COVID-19. Okay, and the dashed arrow from infectious group to the susceptible group means the individuals in the susceptible group can be infected by the individuals in the infectious group with a certain rate, and this rate is denoted by beta, which is called the contact rate. Okay, and from the infectious group to the removed group, there's a ratio which is denoted by gamma. So gamma is called the transmission rate from the infectious group to the removed group. Okay, so this characterizes how fast the individuals in the infectious group can, for example, recover, can be cured by some, for example, medical treatment, or can die from the disease. And the corresponding dynamics for SIR model is characterized by the systems of ordinary differential equations. So on the right, you can see a system of ODE, which you have ST, IT, RT. So these are basically the number of individuals in each of those group. Okay, and we calculate the time derivative of the of ST, IT, and RT, which is driven by those model parameters as well as the number of populations, which is denoted by big N. Okay. So the second model is called SEIR model. So compared with SIR model, the SEIR model adds an additional compartment, which is called exposed. So the reason people add this compartment is because for many diseases, there is an incubation period. Okay, so during the incubation period, the individual, he or she has already got exposed to the virus, but he or she hasn't developed the symptom. So therefore, it's more like a silent patient. You don't know, or they don't know they got infected. Okay, but later when they further develop the symptom, they will get transferred to the infectious group. Okay, so given this additional exposed group, so there's an additional delay between the individuals in the susceptible group who got transferred in the infectious group. And because of this additional group, so we will introduce another ordinary differential equation, which is a DET divided by dt, so time derivative of ET. And I'm not gonna go over each of these ordinary differential equations line by line because they can be derived by this compartment picture. Okay. So what I want to emphasize is there are several limitations of SIR and SEIR model. Okay. The first limitation is both of the models, they don't take into account the untested or unreported cases. Okay, so if you look at the picture, there's no mechanism that can consider the unreported cases in the population. And also, neither of them take into account the silent spreader, which are individuals who don't have obvious symptom. And this is also a limitation of existing SIR and SEIR model. So based on these motivations, we proposed a new epidemic model. We call it SUER model. Okay, so here U represent the unreported cases. So we modified the standard SEIR model by adding an additional compartment, which is the purple one. We call it unreported. Okay, it contains both unreported infectious and unreported removed individuals in the population. And in addition to that, we also add another arrow from exposed compartment to the susceptible compartment, because according to many studies, even for individuals in the incubation area, they already contagious, so they can infect individuals in the susceptible group. So that's the reason we add additional infection path from the exposed compartment to the susceptible compartment. So these are the two key features we introduced in our model, which account for the unreported and untested cases, as well as for the so-called silent spreaders. Okay, and because of this additional unreported component, we need to introduce another parameter, which we call it discover rate. Okay, because of doing testing, we will be able to discover certain portion of individuals who got affected by COVID-19, and therefore they will go through this path. Okay, but since many individuals, they don't have any symptom, that's why they don't got tested, and they will go through the other path to the unreported component. Okay, and the discovery rate is denoted by mu. Okay, and this parameter actually depend on the testing capacity. Okay. And based on this picture, we are able to write down the corresponding systems of ordinary equations. Okay, so this system of ordinary equations correspond to our model. Okay, so basically speaking, for example, if you look at the first ordinary differential equation, the number of people which are moved from susceptible to the exposed component actually is proportional to the contact rate times IT plus ET. The reason is both individuals in the infectious group and also the exposed group can affect the individuals in the susceptible group. Okay, so for the remaining ordinary differential equations, I'm not gonna explain it in very much detail because it won't affect you understand the key idea of this model. So given the model and the corresponding ordinary differential equation, we can using machine learning approach to train this model, to build the forecast model. So this is the machine learning pipeline we are using to train this SUER model. So at the beginning of this pipeline, we take the initial S0 and E0, which are the initial susceptible population and also initial exposed population for a certain population, for example, for the population in a state or for a population in a country. And we also take the daily reported active cases and the daily reported deaths and the recovered cases, for example, from NY Times or from Johns Hopkins data repository. So these are all observed data we can use. And we take all this data as input and using some machine learning method, in particular empirical risk minimization method, to minimize certain loss functions we defined to characterize the goodness of fit of our model to the reported data. And after that, we will be able to get the estimate of our model parameters, including beta, sigma, mu, and gamma. Okay. So once we have these model parameters, then we are essentially having a model that we can use to forecast the future predicted active cases, as well as the future predicted deaths and recovered cases. So these are the basic machine learning pipeline we are using to train our model. And here is a little bit more details about how to train the model. So first of all, given the initialization of S0, E0, I0, and R0, and the initialization of the parameter beta, sigma, mu, gamma, we can use some ODE solver to calculate the estimated active cases, I hat 1, I hat t, okay, and also the estimated removed cases, R hat 1, R hat 2 until R hat t. And we are using the following log loss to characterize the estimation error of IT based on I hat t, as well as the estimation error of RT based on R hat t. Okay, so remember that here I hat denote the estimated daily cases, and the R hat denote the estimated removed cases. Okay, and the data we are using, as I mentioned before, mainly from the New York Times data repository for state and county level models. And for the country level models, we are using the data from the Johns Hopkins University CSSE Center. Then the next question is, can we model the social distancing or stay-at-home order in our modeling process? Okay, and how does the social distancing and the stay-at-home order affect the spread or the spread of the COVID-19 disease? So in our modeling, in order to take into account the social distancing or other public health measures, we introduced so-called ratio parameter, which is denoted by delta. Okay, so in other words, at the initial generalization stage of our model training, we define the sum of the S naught, E naught, I naught, and R naught equal to delta times N. So here, N is the number of population in a state or in a country. But because of we are doing social distancing, we are doing, for example, stay at home. So not all the population will be susceptible to the virus. So therefore, we introduce this delta parameter, which is a parameter between 0 and 1 to denote the ratio or the fraction of the population that is susceptible to the coronavirus. And the next question is how to project the number of deaths, right? According to our model, both recovered individuals and the died individuals are in the removed compartment. Okay, so in order to project the number of deaths, we need to split the removed group into two parts. Okay, so one part contains those individuals who get recovered from the disease, and the other part are individuals who died from the disease. However, how to determine the ratio between the recovered and the died individuals is not trivial. And in our modeling, we introduce a ratio function, which is an exponential function. It has two parameters, A and B. So RT is a ratio of daily increased deaths versus daily increased deaths plus recovered cases. Okay, so we need to estimate these two parameters, A and B, to estimate the ratio of daily deaths versus the daily deaths plus recovered cases. So this is illustrated in this picture. So basically, the individuals in the infectious group will be divided into two subgroups. One corresponds to the recovered individuals, the other corresponds to the died individuals. And in order to estimate the parameter A and B in the exponential function, in the ratio function, we collect the data for US, for China, for France, and Italy. And because we have a very good amount of data for these 4 countries, and we basically estimate the parameter A and B based on the reported data in these 4 countries. And we also compare the predicted removed cases, which are the recovered cases plus the deaths, versus with the ground truth, the reported number. And you can see that using our estimated ratio function, we'll be able to estimate the removed cases very accurately from these figures. So this is how we project the number of deaths. And finally, in addition to point estimation, we also need to provide the confidence interval because this is like a scientific research rather than some thing we just do it for fun, because it's very serious research. So we are using the likelihood ratio test to construct the confidence interval. So once we have the learned model parameter theta naught and some, for example, candidate parameter theta height, we can construct the test statistics in this way, which is 2 times the loss of theta naught minus loss of theta height. And we can show that this test statistics follows chi-square distribution with degree equal to 4. So therefore, we can try different theta height and compare the value of the test statistics at theta height with 1 minus alpha quantile of the chi-square distribution to determine the confidence intervals for theta height with confidence level equal to 1 minus alpha. So this is how we construct the confidence interval in addition to our point estimator. So putting all those pieces together, we will be able to forecast the number of confirmed cases as well as the number of deaths in different levels, including the national level, the state level, and the county level. So for COVID-19 forecast in the national and the state level, we collaborate with RecLab at UMass. They have a so-called COVID-19 forecast hub, and they collect the predictions from several different universities and national labs, and put them together, do some kind of ensemble learning to ensemble the projections made by different parties. And the individual model as well as the ensemble model is later utilized by CDC forecast to forecast the national cumulative deaths on a weekly basis. So as you can see, our model is one of the 12 models used by CDC for the national level and also state level death forecast since 3 weeks ago. And let me give you some comparison of our model, of our forecast result with other results generated by our other models. So this is the predicted number of deaths in the week of May 5th to May 11th. And the first row is the number of reported deaths in the United States. And each row actually is the forecasted, is a projected deaths by different models. The IHME model is the very famous model, which is developed by IHME, the institute in UW. And this model has been repeatedly referred in different news articles. And you can see that in terms of prediction accuracy, their model actually is not very accurate. So here we, for each day, actually, we use the absolute difference or absolute error to measure the prediction accuracy for each model. And there's a rank on a daily basis. And we are using the border rank aggregation method to combine these daily rankings over the entire week to generate the final weekly rank. You can see that in the week of May 5th, our model is ranked second in terms of death projection in the national level. And the IHME model actually is not ranked very high. And in the following week, in the week of May 12th, the projection by our model actually is the most accurate among these 7 models. And our model was ranked the first. And the IHME model actually is only ranked the 7th. So this is some preliminary comparisons among these different models. So we will see what's going to happen in the next few weeks, because we are doing this kind of comparison on our website on a weekly basis. And I also collaborate, and other faculties at UCLA, because they have a very cool project called Stop COVID-19 Together project. They collect the survey in different states, in different counties, including the Los Angeles counties. And they want to use the data from the survey to have a better understanding about the spread of COVID-19. So we collaborate with Iran and other people in this project, and we provide the county level forecast. So here we calculate the projected number of deaths and also confirmed cases for those top 150 counties in the United States that have been hit by COVID-19 most severely. And if you go to their website, you can click on different counties, and there's a forecast figure showing up on the left. And they use both our projection and also the IHME forecast, because that's the most famous one. And based on our evaluation, so sometimes our forecast is more accurate, while the other times maybe IHME model is more accurate. Because this is in the county level, there are not so many training data. So the forecast of the deaths as well as the confirmed cases is much more challenging than the forecast in the state level and the national level. Okay. So in many of us, I will briefly go through some other things our model can do beyond deaths and confirmed cases forecast. So the first thing we can do besides the death forecast is a peak date estimation. Because in our model, if you just count the number of individuals in the infectious group, then you will get the number of confirmed active cases. So these are the people who are infected with COVID-19. They are either hospitalized or stay at home, but they are not fully cured and recovered from the disease. And this kind of information is particularly important because the number of required medical resources is somehow proportional to the number of confirmed active cases. So it's important to have a very good estimate for the number of active cases. And based on number of active cases, we can predict the peak date for United States as well as for different states. For California, as you can see, according to our projection, the peak date in California will be on June 25th, in a month from now. And we also have the estimated peak date for United States and all the 50 states in the United States. And for United States, you can see that the peak date is on May 31st, which is just a few days, in a few days. And if you look at the peak date for New York, actually New York already passed its peak date. And this is very true if you look at the number of confirmed cases in New York State. That number actually is keep decreasing in the past 2 weeks. And another thing we can do is to estimate the so-called basic reproduction number, which is called R0. Because R0 denotes the expected number of cases generated by one case at the beginning of the outbreak. So to give you some example, for Ebola virus, the R0 equal to 2, roughly equal to 2. And for SARS, the reproduction number roughly equal to 4. Okay. But based on our model, actually we can also estimate the basic reproduction number. So in order to estimate the basic reproduction number using the technique called the next generation matrix, which I will skip the details. So basically we need to calculate we need to define two vectors, f of x and v of x. So both of them can be seen as a vector valued function whose parameters are st, et, it, and rt. And we can calculate the Jacobian of the partial Jacobian matrix of these two function vector valued functions. And then we can calculate the next generation matrix based on the partial Jacobian matrix. By doing some kind of mathematical derivation, we can derive the basic reproduction number for our model, for the SUER model. It equals to beta divided by sigma plus beta mu divided by gamma. Okay, so this is the reproduction number corresponding to our model. And since we have a very good estimate for the model parameters of our model, we can immediately estimate these R0 based on the estimated model parameters. So here are the summary of the estimated basic reproduction number for different states as well as for United States. You can see that based on our estimation, the R0 in US is about 2.5. Okay, so this number actually is slightly higher than Ebola, but actually is much lower than SARS. But in some states like New Jersey and Massachusetts, actually the R0 is higher than 4. One is 4.5, the other is 4.2. So both of the estimated R0 in these two states are higher than SARS. Okay, and that's the reason why the New Jersey actually is hit by COVID-19 very severely. You look at the number of confirmed cases actually is declining very quickly. So it still maintains at a relatively high level because it has a very big R0 at the beginning. And for New York State, the R0 is about 3.6. Okay. And R0 is the reproduction number at the beginning. So at the beginning of the outbreak, right? So we also want to monitor the dynamic of the reproduction number because ideally it should be decreasing. And how fast it decreases actually reflect the effectiveness of the public health intervention in that region. Based on our model, actually, we can calculate the RT, which is the effective reproduction number on data T. Okay, so this is calculated in this formula. So you can see that at the beginning, RT equal to R0, and it's greater than 1. And it may first, when RT is greater than 1, actually, the number of infected individuals will increase. And after RT gets less than 1, then the number of infected individuals will decrease. Okay, so we can estimate the RT curve for the states, for different states in the United States. So here I give you 2 examples. One is the RT, the effective reproduction number in California. So as of today, you can see that the reproduction number in California is still higher than 1. Okay, so this is not a very good message because that means we are still in a very high risk time period because each individual, each COVID-19 patient may still be able to infect more than 1 individuals in the population. And for New York, as of today, the reproduction number is already less than 1. So that means the number of infected individuals in New York State actually indeed start to decrease. So you can think about the curve which I showed you on the right of the slide. Because when RT less than 1, that means the growing of the infected individual actually becomes slowing down, and sooner or later the peak date in that state will arrive. Finally, I want to talk about how to calculate the prevalence. So prevalence means the proportion of a population who has a specific, for example, disease in a given time period. Okay, and according to the definition I borrowed from NIH, in order to calculate the prevalence, we often do a subsample of the entire population because we are not able to test every individual in the population. So we have to sampling, do subsampling. And based on that sample, we can calculate the number of people in that sample with disease divided by the total number of people in that sample. And in this way, we can calculate the prevalence for COVID-19 or for other diseases. And the typical way to estimate the prevalence is using antibody test, or sometimes called a serology test, which looks for antibodies in blood made by the immune systems. And actually, in New York State, they have already done the antibody test among healthcare workers in several different counties. And you can see that, for example, in New York City, the prevalence among the health workers is about 12%. And the prevalence among the general population is about 19.9, almost 20%. So this is a very, very high number for prevalence. That means a lot of people in New York State have already got affected by COVID-19, no matter they are patients with symptoms or they are asymptomatic individuals. And using our model, we can also estimate the prevalence without using the antibody test. Of course, I I'm not saying that using our model can replace an antibody test. I want to emphasize that our model can be used as like additional information or additional evidence to provide a very reasonable estimate for preference in different states. And according to our model, we can estimate the preference based on ET plus IT plus RT plus UT divided by the number of populations in that state. And based on this, we actually estimate the preference in different states in the United States. So this heat map is the estimated preference in different states in the United States as of May 23rd, just 2 days or 3 days ago. And you can see that the estimated preference in New York is about 19%. So this number actually is very, very close to the number reported in New York State based on antibody test. And there's a very interesting study by a group of people in USC. So they have done antibody test in Los Angeles County among adults on April 10 and 11. And this paper has already published in JAMA, a very good journal in medicine. And according to their study based on antibody test, there are about 4% population in Los Angeles County who got affected by COVID-19. And based on our model, actually, we can also estimate the prevalence on April 11, which is about 1.8%. So actually it's lower than their estimate. But on May 23rd, the estimated prevalence in Los Angeles County actually increased to 9%. So if you think that the estimate on April 11 by our model is an underestimate compared with the USC study, then perhaps the estimated preference on May 23rd is also underestimated. But this is just something we need to think about it, and we cannot draw a conclusion from this kind of number, but it's definitely of importance to further look into different information sources, including our estimation, to have a better estimate of the preference in Los Angeles County. Okay, so finally, I can also use the model to study the effect of reopening, right? So one idea is we can introduce another in-link to the susceptible group, which models the, for example, the fraction of the population that will be under the risk of being affected by COVID-19. And we can define some time varying, for example, curve to modulate the increase or the decrease of the susceptible individual in the susceptible group. And in this way, we will be able to model the effect of the reopening, as well as other things that may take place in the next few weeks to the next few months. Okay, so with that, I would like to conclude my talk. So basically, I show that by bringing the epidemic models as well as the machine learning together, we can provide more accurate and reliable predictions. And our method can also predict the peak date, the reproduction number, as well as the prevalence. And this information can be used to better understand the severity of the epidemic outbreak. And public policies such as the reopening can also be potentially evaluated on our framework. This is something we are currently working on, and this is still ongoing study before I can share with you more useful information. And in the future, we also plan to study the infection fatality rate, which is the more accurate fatality rate compared with case fatality rate. And we also want to study the discovery rate, which is the number of COVID-19 patients divided by the number of real number of individuals who got affected by COVID-19, including both reported and unreported cases. So we call it the discovery rate estimation. And we also want to understand the effect of intervention. So here are those collaborators and the team members, and we also received some credit from Google Cloud to support our research. And finally, I would like to thank all those healthcare workers, because they are the real heroes working on the front line of this battle. And I'm just the person working in front of my computer to provide some information to inform the public as well as some government agency about the current situation. Thank you.
Thank you. Thank you, Kwang. Any questions? Anybody? Somebody can see who asks questions and enable it. How does it work? Okay, we have a sequence of questions on the waiting on the questions and answer. An anonymous attendee, can you explain the dotted, so this is something about the past, do the dotted line signal about the past?
Okay, yeah, so.
Oh, you can see the questions, okay.
Yeah, I can see the question, yeah. So regarding this figure, so the solid line, you can see that today is May 26th. So the solid line actually is the real number of reported cases and the real number of deaths, okay. And the dashed line actually is the projection, because for example, on May 27th, on tomorrow or in a week or in 2 weeks, what will be the number of confirmed cases as well as the number of deaths, right? So these are something we don't know. So that's why we need to project. And we use dashed line to denote this is a projection. And this shaded area is the confidence band, because as I mentioned before, in addition to point estimation, we also provide a 95% confidence interval for our projection.
Okay, you see there is many other questions. You see them?
Yeah, so let me read the question. So do the dotted line signify moving between compartments or interaction with people in those other compartments? Oh, I think this is about this one. So I think what does this dotted line mean, right? So this dotted line means, for example, the individuals in the infectious group can infect individuals in the susceptible group. And here, similarly, the individuals in this compartment can infect individuals in the susceptible group. And for our model, you can see that there are 2 dashed lines. One is from the exposed group, the other is from the infectious group. So that means both individuals in the exposed group and infectious group can affect individuals in the susceptible group.
Then you have some, go ahead.
Oh, please go ahead.
I thought that you finished, sorry. If you didn't,
there
is also questions on the chat, not only on the questions and answers.
Okay. Yeah, I think there are several more questions. Since Delta and Sigma typically change over the course of a pandemic, would it be a good idea to try to model the change in Delta and Sigma? That's a very good question. So far you can see that no matter in SIR model and SER model, or in our model, we basically treat beta, mu, sigma, gamma, these parameters as a constant. It's not a time varying, actually it's a time invariant parameters. And we were thinking about how to make it as time varying parameters. The key challenge here is once you make it as a time varying parameter, then the number of parameters in our model will grow as the, for example, number of dates, right? So in that case, we may have much more number of parameters than the current 4 parameters. So based on the data, based on the availability of the data. If we have a lot of data, we can of course do that. If we don't have much data, then probably by introducing more model parameters may not give you better, more accurate projection. But that's a very good future direction. Did any of the modeling take into account the possibility of reinfection? Okay, so that's a good question. For SIR and SER as well as our model, we assume that there's immunity for an individual after he or she recovered from the COVID-19, maybe within the next several months or several years, he or she won't get infected again. So that's the assumption we are making currently. So there's no, for example, transition from the removed compartment to the susceptible group. And next question, how could you model state or county level public health prevention measures like social distancing, reopening of stores? Would this be an adjustment in the parameter in the model or modification to the compartments? Yeah, that's a very good question. So actually I briefly mentioned the two modeling technique. Okay, so one modeling technique is instead of considering all the population, so putting all the population in a state or in a county into the susceptible group, we only put a fraction of the population in the susceptible group. And this fraction actually depends on the public health prevention measures. So for example, if in a county, these measures are well implemented, then we will have a very small data. That means only a very small fraction of population is susceptible to the virus. And also, I briefly mentioned that we can introduce another in-link to the susceptible group. This is just like for example, the birth rate or the death rate. So we assume that if, for example, we reopen in the next few days or few weeks, or if we have already reopened, then there will be more people gradually, for example, transferred into the susceptible group. And this rate actually is characterized by alpha t. And alpha t actually can be defined as a step function, where the jump of the step function actually can be placed on the date of reopening or a week or 2 weeks after the reopening. So you can decide how to design this step function. And the step function is the simplest function. You can also use more sophisticated function to describe the impact of the reopening. Next question, aren't antibody tests very error prone for calculating preference, especially when used in less affected regions? So, because I'm not an expert in serology, so I cannot say whether antibody test is sensitive or not, or whether it's reliable or not. So there are different kinds of antibody tests developed by different companies. I would say that antibody test is probably the best way to estimate the preference if we can test every single individual. But the reality is impossible to test every single individual. So we have to do subsampling. We have to come up with some testing strategy to test a subsample of the population. And you are right, maybe antibody test itself is not very reliable. There are some false positive rates or some false negative. So in that sense, I think our model can be used as an additional information source or evidence to complement the antibody test-based preference estimation, because our model does not depend on antibody test, and we can estimate the preference just based on our model without doing antibody test. But I think the best way is to integrate these several strategies together instead of just using one of these estimate. So this is usually the case when we have different kind of information sources. The ensembled one usually performs the best, or the ensemble one is more or less the most robust estimate. And a question from Jason, can you calculate when the active cases be less than 1%, say in US and in LA? Yes, we can calculate that. Actually, if you go to our website, we show the curve of the active cases. It first go up and then go down, and there's a peak. And if you go to the very left of the plot, oh sorry, very right of the plot, you will see when the cases will be less than certain percent. But for the purpose of visualization, we may not, we probably didn't plot the curve until the active cases is less than 1%. But this information is definitely contained in our forecast, and we can definitely add this kind of information onto our website. And we have another question from Wei. Do you consider number of hospitalization as a separate variable in your model? The transmission and the disease progression for those patients can be quite different. Yeah, that's a very, very good question. Actually, currently we don't differentiate the patients which are hospitalized versus those patients which just stay at home receiving some medical treatment. They are indeed very different patients. And for example, the fatality rate can be very different. And also for example, the length of the period that they have symptom may be very different. But so far we haven't considered this difference in our modeling. It could be a very, very important direction to explore in the next step. Next question is, could you explain again, how do you get the confidence interval? What's the difference between candidate parameters and the learned parameter? Sure, let me explain it again. So let me go to the, okay. So in order to calculate the confidence interval, so we can do, for example, word test or likelihood ratio test or score test, right? So these are the three classical test statistics based on which you can construct the confidence interval as well as calculating the p-value, right? So here we use the likelihood ratio test because our estimator is based on, for example, minimizing this kind of loss function, which can be seen as the log likelihood of some model. So that's why we use likelihood ratio test. And for likelihood ratio test, once you write down the test statistics, you can prove that according to some literature, including our own paper. You can calculate, you can show that the test statistics asymptotically follow a chi-square distribution with degree equal to 4. Okay, so that means when the number of samples is sufficiently large, this follows like a chi-square distribution. And here we assume the null hypothesis is the theta naught, which is the estimated parameters in our model. So this is an estimator. And you just want to perturb our estimator, for example, to left or to the right in an element-wise manner to find the confidence band for our prediction. And we can, for example, just try, for example, theta naught plus delta. Delta is the perturbation. We just try this perturbation by using some kind of grid search method. And once you find a theta height, for example, which is a perturbation of theta naught, such that it falls in the, for example, 1 minus alpha quantile of the chi-square distribution with degree equal to 4, then we will be able to use that theta height as the, for example, 1 minus alpha or alpha confidence, 1 minus alpha confidence interval for the estimate of our parameters. Okay. Of course, you need to convert the confidence band for the parameters into the confidence band of our forecast. So there's still some derivation between this confidence interval and the predicted confidence interval. But what I said is the basic idea, how to use the likelihood ratio test to derive the confidence interval. And the next question is, my question will answer later in the present. Thank you. Okay. Is there a guided model from Paul? Is there a guided model that takes into account the unreliability of the data sources? For example, some justifications are widely suspected of underreporting cases. Can your model take into account this? Okay, so we didn't explicitly consider the reliability of the data sources, but we do consider the case that in all the counties or in all the states, we believe the number of cases are underreported. So that's the key motivation we add this additional group or additional compartment, which is called unreported. So in other words, you can see that only a fraction of individuals in the exposed group will be transferred into the infectious group. And this corresponds to the individuals that has been tested as positive, right? But there are a lot of individuals, they got exposed to the virus. They actually got affected by the virus. But because they have very mild symptoms, or because the testing capacity in that particular region is not good enough, then many of the individuals, they didn't receive test, and therefore they will move into the unreported cases. So this is the idea we are currently using to model the unreported cases. But I believe there are many other ways to take into account the unreported cases, or even consider the reliability of the reporting systems in different counties, in different states. I think that's a very good research question for future. Yeah. And another question from Wei, can your model predict when the second wave will come and how bad it may be? This is something our current model cannot do. And actually in the future work slide, I mentioned that we will try to understand the effect of intervention. Actually, this includes the effect of reopening. And we plan to do some kind of causal influence. Actually, I'm not an expert in causal. Our colleague Julia, he's expert. Maybe I should talk to him more about this, because this is more like a what if question. So what if we remove the stay-at-home order? What if we reopen? Then what would the, for example, number of confirmed cases and deaths will behave, right? So this is like a causal influence problem. I think it's a very, very important question. Many people would like to know, but currently I don't have a very concrete idea how to do that. And we are still thinking about how to model this kind of intervention or how to predict the second wave by modifying our model or by proposing new model. And the next question is, how does this model, Ali, do you have any question?
The question is how long we are going to take questions, because people are dropping. We are we now have we are by a factor of two, by a factor of half. We are half where we started.
Yeah.
So I wonder, usually it's an hour, but
yeah.
If you want, yeah, go ahead.
Yeah, we have 3 more questions, and after that, maybe we can, yes, stop. Yeah, just 3 more questions, all from anonymous attendees. So how does this model take into account in the next few days, the state will be lifting lockdowns and restriction? Won't this affect the susceptibility and the infection rate? Yeah, I think that this question is very similar to Wei's question. We are currently thinking about how to take into account this kind of factors, but we don't have very concrete ideas yet. But this is indeed a question we need to solve. The second and last question is, what widely available facts could you integrate? For example, population density, age distribution, income to predict outcomes. Okay, that's a very good question. So I totally agree that for example, the contact rate or other parameters in a model highly depend on the, for example, the mobility of the, for example, people, right? Because this past the long weekend, many people, they went to beach or went to the, for example, trails, parks, and according to Google and Apple, actually, they are currently doing some kind of mobility detection or estimation, and they also make their data public. So I think that kind of data can be used as a source of contact tracing, or a source of, for example, like mobility data that we can leverage to improve our model. But regarding the population density, the age distribution, and the income, I think these are also very, very important factors. But currently, we don't have a very good collection of the data in terms of, for example, age distribution, income in the state level. In the county level, we do have this kind of data. We can collect the data from the Department of Public Health in LA. But in the state level, we need to collect this data from different counties and then aggregate them together. And this kind of aggregation requires some extra effort. We haven't done that, but we do have a student working on that. Actually, after we initially launched this project, we recruited quite a few undergraduate students working on this project, and they are currently collecting this kind of data. And hopefully, after they finish the data collection, we will do some kind of cleaning, and then we will be able to aggregate them together to use as a feature for our model. Okay. And the last question, not specifically for your model, but for all models in general, that's a very good question. How do they account for the second wave of infection? Is it just all handled by 4 constant parameters being refitted? Yeah, so I think this is also related to previous question by Wei and the other audience. I think in terms of accounting for the second wave, this is something many people would like to know. I also would like to know. But I think it's more like a hypothesis testing or causal inference problem rather than correlation analysis. So in this sense, I think our model needs to be substantially modified, or even new models are required to do this kind of second wave forecast. But I also see other people, they made some very brave forecasts about the second wave, or very wide forecasts for second wave. I don't know what what kind of model they are using. So it might be interesting to also to read those things in detail and to get inspired by those things. I'm not saying they are not doing a good thing. I'm saying they are doing something I currently don't have a very good understanding. So I would say I will look into this in the next few weeks, because we still have time. I don't think the second wave will arrive in a month or in 2 months. So what I'm talking is more like after 3 months or after 6 months, there will be a second wave in late fall or in the winter, right? So we still have time to think about this question and to develop a more powerful methodology to predict the second wave. I
Okay.
think that's quite
Yeah.
yeah.
Okay, so you were, is there any other questions? Because we stayed. So I will put another question.
Sure.
I missed it completely. You call it, and I alluded to it at the beginning. You call it machine learning, but if you have something for which you can write differential equations.
Yes.
Now, you and I may differ whether this equation or this element should be captured by the differential equation or not. But this is nothing. When you say model and you call the differential equation models, this is not about machine learning. This is about how do you model, how do I am model, and you have to explain to Ryan the reason why you think that you can write a better differential equation to capture the COVID-19 better, let's say, that Rich Core's wife, who is spent her life on epidemiology and how you capture and the right way to capture or whatever. So you didn't bring to the table something that I know how to model through differential equations. So you wrote some differential equations. Do we bring the machine learning into play because we don't know how to solve these differential equations, and therefore we use some machine learning, some neural nets to solve these differential equations? Or you say, no, I have differential equations and I have also data and I combine them. I completely lost about the question, where is the machine learning and where is your type of expertise comes here to say, I have a model, while there are people that dealt with modeling epidemiology for years and years. So if you say, I can solve Maxwell equations with machine learning, doesn't make you an electrical engineer. So I completely lost about what happened here.
Okay, yeah. That's a good question, and I wish you can you answer this question earlier, but I think it's a good time for me to clarify it. You are right. So I position this work as an epidemic model guided machine learning, because as you mentioned, at the core of the forecast actually is this new epidemic model we proposed, which is called SUER
You propose
model.
a new model,
is an
that's
epidemic
okay.
model, which is a mathematical model. So
right.
this is not machine learning.
New mathematical models, that's okay, but this is not your area of expertise. You propose new mathematical model. It may be good, it may be bad. Maybe you were lucky and you proposed a very nice model, but this is not something that is what you did a PhD about or anything like this. So go on. So where is your PhD and all your expertise comes into
you're
play?
Right. Yeah. Okay. So I think this is a very new area, because epidemiology actually is a very well established and well developed discipline, right? But you know that we have so many different data. The data actually are overwhelming these days about the COVID-19, and how to leverage this data, and also how to borrow for example, the very good knowledge developed in epidemiology, how to integrate those things together, actually is a new area, I would say. Because for epidemiologists, they are expert in these things. I'm not expert, they are expert. But they may not be able to, for example, train 100 models or 1,000 models a day based on the data, and also based on their epidemic models.
So your expertise is to take the data and
this is
okay. So your expertise is say, take
the
data and from the data propose this model. This model was not just you dream a differential equation, but the data drove you to your analysis of the data drove you to come up with this model of differential equations. Is this the case?
No. The case is the model actually is proposed based on my understanding about the features and the uniqueness of COVID-19, of the coronavirus, because traditional epidemic model like EIR or SIR, so these are very, very classical mathematical model for epidemiology. But when people propose these two models, the context actually is different. It may be for some other disease, but this COVID-19 coronavirus is called a novel virus. It's a new virus, and there are many important features, and these features cannot be well described or captured by existing mathematical models for epidemiology. So that's why I propose a new epidemic ER model, which I think can better capture the unique properties of And regarding the machine learning component, I would say that once we define this model and use the ordinal differential equation to describe or to characterize the dynamic of this model, we still need to learn the parameters of the model, right? And this estimation or parameter learning process is done by machine learning, because we are not just manually tune these parameters. Actually, we use the data to fit the model and then to learn these parameters simultaneously. So basically, we go back and forth. So given, for example, a set of parameters, we use ODE solver to generate the reported cases, for example, confirmed cases, reported deaths. And then we compare the projected, for example, confirmed cases and deaths with the reported confirmed cases and deaths. So this is more like a back propagation and forward propagation. So based on model, we do forward propagation, we get the projected numbers. And then we compare the projected numbers with the reported numbers. We see some error, and then we back propagate the error into the model parameter to get the gradient of the model parameter. And then we do gradient descent in the parameter space. So this is like a go back and forth machine learning process. So this is the place where machine learning comes into play. But maybe you don't want to call it machine learning, you want to call it statistical analysis or data science or whatever. I think that's totally fine. Because as I mentioned, the AI, machine learning, data mining, data science, big data. So these things, I think they are essentially integrated with each other. So we cannot say this is the AI, this is the machine. We cannot differentiate them. Maybe at certain levels, there's still some difference. But in the most general people in these several areas, they are all dealing with very similar things using very similar tools. So
I see. So this was, you didn't, you see, in emphasizing the differential equations, this is not your area of expertise, these differential equations. What you say is jumping between the data and the model. I can see, I understand this is also what Professor Song Chu probably is doing, you know, taking, putting the machine learning, which we don't understand well, into the statistics, which differential equations we understand well. Okay, so but the combination of these, but I didn't exactly see it because probably it's, I didn't learn it. Okay.
I think, yeah. Even for differential equation, actually, I've done a lot of work on MCMC and stochastic gradient Langevin dynamics. So those things are all about differential equation or even stochastic differential equation. So I do have expertise in ODE and SDE, but I'm not an expert in epidemiology. So that's why I collaborate with people in UMass, because the lead of that project, actually, he is like a epidemiologist and a statistician. So yeah, I also learned from my collaborators. Yeah.
Okay, thank you very much. It was quite interesting. Now we are the third of the people, so that's, but we had still third.
Yeah.
Thank you all very much for coming.